the second unit of condenser. So now, earlier we were having only one air-cooled condenser in service. Now we have two air-cooled condensers in service. So let's talk about sustainability. NTPC North Current is in Jhajjar, which marks a milestone as having India's first air-cooled condenser. It is installed in a supercritical plant, demonstrating NTPC's commitment towards water conservation through the 3 R's, that is reduce, reuse and recycle. The project has been envisaged with air-cooled condenser, that is ACC, which has almost 1/3 the water footprint as compared to a conventional water-cooled condenser. This results in water saving of around 30.5 MCM, million cubic meters annually, thus fulfilling the needs of around 3.5 million people in the region. The groundbreaking initiative not only signifies technological advancement, but also underscores NTPC's commitment to sustainability, offering a blueprint for water-conscious and efficient future. So far, I told about the air-cooled condenser, but then air-cooled condenser is not a solution to all the evils. We'll see in the subsequent slides. So let's see, how does an air-cooled condenser work? An air-cooled condenser is a direct dry cooling system where steam is condensed inside air-cooled finned tubes. The cool ambient air flow outside the finned tubes is what removes heat and defines the functionality of an ACC. Those who have worked in a gas power plant also know that in a gas power plant also we have what is called as fin fan coolers. Fin fan coolers are again something of a similar type, whereas in basically equipment cooling and other cooling we have water-based coolers. In gas power plants we have air-cooled coolers. So similarly, ACC is a bigger version of the same. In thermal power plants, the steam from the turbine exhaust flows through the ACC, where condensation occurs. Thus the condensate returns to the boiler in a closed loop. Since the steam coming from the turbine is at a low pressure, the ACC works at a pressure close to vacuum. However, as we know, the specific heat of water is almost 4 times that of air. So the volume requirement becomes very huge. And non-condensable gases are removed continuously by an air evaporation plant. So this is the ACC plant. You can see there are fans below the ACC plant which help in circulation of the air, ambient air, which causes cooling. These kinds of power plants which are equipped with ACC do not require a large volume of cooling water. The power plants are easily be built in a region where water may not be available or water availability is scarce. So this is basically the crux. That, as one of the earlier speakers told, that we have to take a holistic view of the scenario. Whether water is available, because now there is a dilemma, there is a decision to be taken, because in case you go for an ACC or air-cooled condenser, the coal consumption will slightly go up. That is, the heat rate will slightly go up and the vacuum will be poor, but water consumption will go low. In case you have a water-cooled condenser, the heat rate is better, the vacuum achieved in the condenser is better. This is the picture of the direct dry cooling system in which steam is condensed under vacuum within air-cooled fin tubes. You can see this is the picture of the air-cooled condenser. So there are fans below the air-cooled condenser which is sucking the air, and the steam is coming in the air-cooled condenser, ultimately getting The main components of ACC are ducting, fin tube heat exchanger, axial fans, motors, gearboxes, piping and tanks. Ambient air travels over a fin tube heat exchanger. Again, to increase the heat exchange area, we have a fin tube heat exchanger utilizing a force-shaft axial fan to condense the steam. North Karanpura ACC is based on SRC, that is single row tube A-frame air-cooled condenser. So there are 10 A-frame type streets of fin tube elements. Each street contains about 9 modules. Each module is composed of bundles of fin tubes. So this is basically North Karanpura arrangement. ACC tube bundle details. So the major components are the main exhaust steam duct is directly connected with hot box and LP turbine exhaust and the steam distribution manifold at ACC end. So this is something just like the conventional condenser. The exhaust steam duct is connected to the LP turbine exhaust. Similarly, here also the same thing. Steam distribution manifold for each speed expansion joints, etc. K-type tube bundles and D-type tube bundles. Condensate collecting ducts for roof rows. Condensate deaerator, storage tank, drain pump. This is a separate thing. Condensate deaerator, because normally we have below the condenser we have a hot well from where the condensate is collected by the CEP. In this case, there will be more collection tanks required. So that is why we have condensate deaerator and storage tanks separately. From there we have drain pump, etc. Fans, gearbox, motors, RCC columns, all these things. So the footprint you can see, the size becomes very large, 132 meter by 131.55 meter. So you can see the volume requirement of the ACC has gone so high. Number of columns 25, number of streets 10. Each street consists of 9 modules, so there are 90 numbers of modules. These are ACC tube bundle details. 63 tube bundles in each half street. Total number of bundles 1,260. There will be 2 types of bundles, K bundle and D bundle. Total number of tubes per bundle is 36. Length of the tube in D is 11.6 meters. Total surface area provided is again a very huge value. This picture shows Unit 1 completed, Unit 2 was under construction when this picture was taken. Now, of course, there are 3 units of 660 megawatt, all with air-cooled condensers. So, Unit 2 has come now, and Unit 3 is likely to come in few more months. This is a picture of steam motor circuit. These are salient features of North Karanpura. These are operating details. It is operating at 15 degrees to 28 degrees. TDD is 3. The desired airflow quantity is very high. Here I have shown a comparison between a conventional water-cooled condenser and a air-cooled condenser. So NTPC Khargone is having 2 units of 660 megawatt with a conventional water-cooled condenser, and North Karanpura is having 2 air-cooled condensers. So water consumption, you will see there is a drastic difference from 40 MCM, it will drop to only 15 MCM at North Karanpura. Unit heat rate, as I said earlier, will go up significantly. At Khargone it is 2070, at North Karanpura it is 2237. So it is a give and take. We are taking on the water consumption, but we have to give away on the specific coal, on the coal consumption, heat rate. Coal consumption, again, at Khargone is only 7.1 million metric ton. At North Karanpura it will be 7.9. CO2 emission ACC area layout. ACC layout. Thank you. I just wanted to share that we have to take a holistic view when we talk about the air-cooled condenser. There is nothing which is okay for one place and is okay for what we say is one size doesn't fit all. So there is no such thing as there is Rampar Dawa. There is nothing like that. So we have to take a holistic view. Once we know, yes, we don't have water, but we have coal. So the only alternative is go for ACC. But if you have water and you have coal, you can definitely go for the conventional water-cooled condensers. For Khargone case, we are getting coal from a distance, but water is available. So that is why we have decided to go for a conventional water-cooled condenser. Any questions we'll have later in the day. Thank you.
Presentation now.
Thank you, Madam Chair. Thanks, organizer, for giving me the opportunity to case what practices we are adopting at NTPC. Jhajjar. Namaskar to all. We had a very sound technical presentation, but here I am just going to describe about what are the saving potentials or what the saving we have achieved at our Jhajjar plant. So basically there are the one or two slides which are main interest here. Other technical aspects we have already covered, but we will touch slightly what are the initiatives at Jhajjar we have taken to save the water. This is all known, cooling water is very essential, very important for the power plant. Just to condense the low grade steam. To maintain the healthiness of the CW system, to optimize between the higher COC and possibility of the scaling or corrosion, we have to have a very selective treatment, chemical treatment. With increase in COC, there is always a possibility of decrease in the cost that I will describe later. In addition to that, I am going to discuss about how to preserve the stagnated water. If there is long shutdown, during the COVID time we have faced it actually, 4 to 5 months units were shut down, and you can just imagine how the stagnated water can create the problems. So how we dealt with that situation, I am going to describe that in 3-4 slides. At Jhajjar we have taken some initiative, already I think all are aware, but I will touch one by one. Increased cycle of consultation through chemical treatment. This chemical treatment program we have adopted or we have designed through our R&D, that is in Netra, NTPC Energy Technology Research Alliance team, that is in Greater Noida, that is the R&D center of the NTPC. They have designed a specific treatment program for our Jhajjar, or in fact for all the stations they have designed, and we have adopted that for last 5 to 6, 7 years. Zero discharge. As it has been said that there is nothing like zero discharge, it is only the conditional which we are adopting within the station by managing our water system. So, in fact, Jhajjar is also a zero discharge plant. We are not discharging any effluent outside the plant. In fact, our CPM, or that is the last storage, that is defunct, and all the valves to go to the outside of the plant peripheries are blind. So there is no as such effluent which is coming or going out of the plant. That is one part. This zero discharge is being managed through the different avenues, that is ash water recirculation system. In this, around 15 to 20,000 meter cube per day we are managing and recirculating again into our system. Liquid waste or effluent treatment plants, which is getting all the waste from our drains within the plants, and through that we are able to manage around 10% of our service water, that is around 2 to 3 lakhs meter cube per annum. That's saving of the service water we are managing through this effluent treatment plant, ETP, which is tube settler basically. Then there are the guidelines to use the sewage treatment plant, but right now we are utilizing this sewage treatment plant with best quality, managing the chemical treatment, LM, chlorine, etc. And that water we are using for our horticulture purpose. Beyond that, there are the guidelines of the STP, which our Praveen Gupta sir and others have described. That is a detailed aspect itself. But we are also trying to, because they are being a governmental company, it is mandated to us and we do. But those modalities are being worked out for the Jhajjar. We have RO plant of the 225 into 2 meter cube per hour capacity, and with that we are able to manage blowdown of the magnitude of the 450 meter cube per hour. It is a 3-stage RO plant. That means almost 85% of the recovery is there and 15% of the effluent, that is the reject, which we are using for our coal handling plants. Dust suppression. Post slurry settling pit is there, which is utilizing those hot drain coming from the coal handling plant, and that is also again recycled to our coal handling plant for dust suppression again. Though that quantity is very small, but we are recycling that too. Rainwater harvesting, which is not touched to that extent, is the real game by which we can get the water neutrality actually. We have one study undertaken with the IIT Guwahati, and they have submitted a report for Jhajjar, and we are going to implement that for our rainwater harvesting. Now I will confine mainly to the cooling water treatments. That treatment is essential to manage our corrosion, scaling, falling, etc. We have to have a 4 or 5 chemicals that can arrest or control our scaling, corrosion, or microweave falling, etc. What are those chemicals? All know, but what we are using, that I am going to describe. COC at Jhajjar, around in 2014, we have started with the 2-3 COC, and then from later we got the design treatment program. Based on that, we got up to 4, and from that time we have gradually or incrementally increased our COC level, and now we are managing around 6. Our friend has told that it is in the Ongul plant, I think 10 they are managing. I will discuss how that is being done. But in Jhajjar we are managing up to 6. So what is the cost benefits that I am going to describe later. COC, you know, it is the TDS of our CW system divided by the TDS of the makeup water. Now there are the different COC measurement. Some are measuring through the TDS itself, some are measuring through magnesium, in terms of calcium, in terms of chloride, etc. At Jhajjar we are managing or determining COC in terms of magnesium, because magnesium is a salt which is stable salt, and it is not or lesser influenced by the external factors like calcium is there, silica is there in our atmosphere, but magnesium is to some extent that is not available. So we are managing our COC or determining in terms of magnesium. So we can say magnesium in our OSC water, or that is CW water, divided by the magnesium in our makeup water will give you the COC. So as the COC increases, our blowdown extent also decreases. It's a known fact. At Jhajjar we have around 250 TDS is there. So at 5 or 6 we are managing up to 1250 to 1500 TDS. We are able to manage without having any scaling or corrosion issues. As far as the chemical treatments are concerned, first we have started long back. Only acid was there to remove all the scalings. Astosopher were used, but then to avoid the corrosion, some chromium treatments were later started to use, but because of the chromium's toxic nature or its environmental impacts, now we are using the non-chromate techniques in our chemical treatment plants, treatments. This, I think, already our earlier speakers have covered, but one or two slides. We have to control this COC. We cannot go infinite or from 6 to 7 to 8 without having any proper or suitable chemical treatment. Otherwise, this will have the impact on our condenser or pipeline systems. There will be a precipitation. The whole phenomenon is only the chemical equilibrium, ionic product and solubility product. Those who understand chemistry, they can better understand that whenever the ionic product is more than the solubility product, precipitation will start and we'll have this problem. So to increase the solubility, we have to use special chemicals or to make them, disperse over the surfaces. Scaling, most common, less important. They are the main factor which influence the scaling. Water temperature. Generally with increase in temperature, all types of scaling increases because it's an exothermic process, and with increase in temperature, the scaling influence also increases. Alkalinity, acidity, physical fouling, flow rate of the cooling water, and other conditions. Scale control, I will discuss. Two, parameters are there or indexes are there which Dr. Gupta has covered actually, LSI and RSI, which can be controlled, which has to be controlled basically. And at our NTPC Jhajjar, we are managing our pH. pH is actually most basic thing, and if you are able to manage the pH in our system, I think most of the problems can be overcome. And we at Jhajjar, we are managing the pH around 7.8 to 8 or maximum 8.2. So between the 0.4 we are managing the whole show. Whenever it is going to the 8.2, we are using sulfuric acid to decrease the pH, and we are never allowing it to go below the 7.8. Fortunately, we have the water which has the from the Yamuna canal, which has the pH around 8.3 or 4, so we are able to manage that comfortably. Corrosion and corrosion causes, this has been covered, or I think all knows. To control this corrosion and scaling, we are using in our treatment zinc. All know zinc is a corrosion inhibitor, and which we are using in the ratio of for the dosing of 0.5 to 2.5 ppm only. Then, to avoid the scaling, there is the phosphorate or phosphate base inhibitor which we use. Beside that, biodispersant fouling, There are the EPRI guidelines for cooling waters. To what extent we can go? Calcium sulfate, what is it tolerable? Because beyond that, somebody is saying 10, but there is a limit. There is a limit shown by or given by the EPRI, Electric Power Research Institute, that up to that extent we can go, and beyond that it is never possible, or it is very, very difficult, because ultimately there is ionic product which will exceed then solubility product, and we are never able to get over that. So these are the parameters, or they are the limitations actually of all the parameters: alkalinity, magnesium silicate, pH, TDS, BOD, COD. We have to control these all. In our system, magnesium silicate is around 5,000, and all the parameters are well within these all EPRI guidelines limits. So we have adopted an integrated cooling water treatment program, scale control for calcium magnesium. We are using threshold inhibitor for phosphorate and phosphate base. TBTC we are using, and organophosphate we are using. For corrosion control, we are using the zinc based inhibitors. For fouling control, we are using biodispersant. They are organic based basically, but they are not non-foaming type we are using. And then to have the microbial control, we are using Cl2, and now that is being replaced in all of us NTPC with ClO2 plant. ClO2 has itself different type of issues which we are facing, but I think that we cannot describe here because it is a longer discussion point. Here are some of the parameters for the seed-only system in the Jhajjar. We have 3 NDCD natural draft cooling towers are there, and our circulation rate is 54,000 meter cube per hour per unit. So these are all the parameters, and we are measuring through 5 to 6 COC. Again, it's a repeat. We are using this treatment program, zinc, PBTC, polymer dispersant for microcontrol CO2 or CO2 now, and biodispersant. Zinc, we are using the ppm 0.5 to 1, PBTC 3 to 5 ppm, up to 10 we can go sometime. Polymer dispersant 5, and biodispersant 3 ppm we are using. Biodispersant we are using at the hold up conditions, other we are using on the blow down basis. So, monitoring of the parameter. We are doing the treatment, but we have to monitor so many parameters on the daily basis, even the shift basis, or sometime on monthly basis. Coupon studies or the tests we are doing, some internally, most of these internally, and some of them like collateral silica, etc. we are managing through external testings. All these are the implication, test methods and testing frequencies which we are adopting at the Jhajjar. So this is the actual data based on our plant. In 2014, we have this much of the blowdown, 86 lakhs 19,840, and when before that it was COC2, so then it was more, even more, but I am talking about when we have adopted the COC4 to 6 regime. So in 2023, we have COC6, and then the blowdown was 51 lakhs around. So total blowdown save in terms of cost, it was 7 crore per annum, and that is a huge cost saving actually, you can understand. For that, we have to have a specialized treatment also, and the whole treatment program we have adopted and given to some agency at 2.5 crores. So still then, I think we can have saving of around 4.5 crore per annum, we can say. And one more factor is that whenever COC is increased from 4 to 6, so cost of the chemical also decreased, because we are using lesser chemical now because blowdown is less, and to treat this fresh or raw makeup, we need lesser chemicals. So in terms of that also, there is some saving of the 75 lakhs which we have faced. So this data will clearly show that the chemical treatment program designed for specific water enhances the COC appreciably and result in big water saving, cost saving, but it has to be designed properly, otherwise we cannot achieve those results. There may be more of the chemical consumption, and that may lead to some other problem, maybe scaling itself, rather than solving our issues. So that is to be designed for some considerable period of time, having seasonal impact also in mind, then only we can design that particular treatment. Because there are the seasonal variation, particularly canal water, we get the turbidity from 8 to even 100, and other parameters are also changing. And if we are not testing or analyzing or monitoring these parameters on the daily basis, we can get issues. Then one case study. During the COVID time, we had plant shutdown for the 4 months. Shutdown means there is no circulation in the system, and then no chemical can be flown. And you can just imagine, when we keep our tap water idle for 4 or 5 days, we get yellowish type of water, some turbid water is there. So what about this system which contains 85,000 meter cube part holding water? So to maintain that, what we use, we monitor the chemical parameters. Suppose we dose today, whatever is required dosing there on a particular day, and then circulate this water through condenser for 1 day only. There is some increase in auxiliary power consumption, but then for 5 and 6 days, those chemicals will be there in the system, and they will start decreasing. Then every 5th, 6th or 7th day, depending on the whatever residual chemicals are there, zinc, PBTC, etc., we will dose additional amount of the these chemicals to maintain our minimum dosing level. So with that, we were able to manage our system healthy for 4 to 5, 6 months, and this is that strategic chemical dosing. Whenever there is some decrease in these parameters, we dose particular chemicals to get the design. In addition to that, we also measured MIC through our laboratories only. TBC, SRBs, those are bacteria are very detrimental for water bodies. So those we measured on continuous basis and we got very good results. After 6 months, there was some overhauling in our system for unit 2, I think, and we got this condenser. Totally clean, there was no scaling, and that was due to the efforts for that particular, long shutdown period time we have taken. So, what is the conclusion for this long shutdown? The optimized and selective chemical treatment is to carried for 4 months. We have maintained our pH, but sulfuric acid dosing was less because there was no blowdown and there was no makeup as such. There was only decrease or increase in these chemicals, and because of that, some variation in the pH was there, but we could maintain the pH between 7.8 to 8.2 with very small amount of the sulfuric acid. So overall, there was the lesser chemical consumption, lesser sulfuric acid consumption, and we could maintain the healthiness of our system for those 4 or 5 months. So, with that, thanks organizers.
Good afternoon to all. This is Sohail from DC Bangalore. And thank you for giving me the opportunity to speak. So, our previous dignitaries speakers already talked about the cooling water treatment system. So, I will not go deep in that. My portion is for closed cooling loop water system for water conservation. As already speakers has spoken about the water conservation main areas. So I am focusing on that only. My presentation includes introduction, challenges, impact, and techno-commercial aspects. What is the conventional water consumption pattern, and what are the advancement that we can do and we are doing, and with that advancement, how we can move forward to reduce the water consumption. That is my main focus on the subject. And next is the proposed advancement and design consultations slide, and then advancement benefit and the way forward, emphasis and suggestions. As we know all, this water scarcity is a critical concern for the thermal power generations. Not only the industrial prospects, but as we all know that 70% water is available and 30% land is available. That we have heard. And it's very easy to analyze, okay, 70% water is available. But fresh water is only 3%. And out of 3%, 1/3 is glacier dies. So fresh water quantities itself is very, very less globally. And because of the environmental changes and because of the the climatic change, like somewhere flooded situation, somewhere crisis situation. So because of the unbalanced situation, we are facing water scarcity, and which is not only impacting the industrial process, as well as it is impacting the human. So if we do in a direction to reduce the water consumption, that will not only help to the industrial process, but also it is going to help directly or indirectly to humanity. So my focus is how we can reduce the water consumption drastically which in the present case we are losing. And I am not telling you that we are losing almost all. From the last 25 years, where per megawatt consumption was 6 meter cube to 7 meter cube was there because of the ash transportation model. Like earlier we used lean salary for bottom ash and fly ash. Earlier 4:1 or 5:1 lean salary was there. So a lot of water consumption, water was there. And then slowly pattern was changed for the ash disposal. And in place of the salary, we have gone for a dry for the fly ash. And bottom ash still we had to take it the salary form. But then recirculation form has developed. So out of the total consumption of the ash system, we are able to now recover at least 60 to 70%. So slowly in the ash handling system, water has conserved. But further advancement is required to reduce further. Now, for what our previous honorable speaker has told about the water conservation in main chunk area. If you see it 2 into 800 megawatts, suppose we are doing one project currently. Their total intake we are taking 3800. Out of 3800, you won't believe, makeup is 3200. 80 is going to city makeup, 80 is going to cycle makeup, portable makeup, something is going for service water, 101. But out of 3800, you believe 3000 is going for makeup. And in 3000 makeup, mainly chunk is going for evaporation. And whatever the evaporation quantity, and we are maintaining the COC, based on that blow down will come. So the main chunk of 70 to 80% is the evaporation loss and makeup, blow down and drift loss. Drift loss is 0.05, so that is less. But blow down is one factor, and another factor is the evaporation loss. If our aim to achieve these losses to reduce, if we are able to, get the success on this chunk of the cooling water, we will be able to reduce. Now currently it is 2 point, government MOF and CE guideline is coming in 2017, 1st January. Based on that, we had to reduce up to 3 meter cube per megawatt per hour. So, and even we are trying to reduce 2.8, 2.6. Presently we are doing one project, there were 2.8 meter cube per hour per megawatt is achieved. So, coming to the next. These are the sum, this you can see on an average it was there like total thermal power generation is 237 gigawatt. So in the present case we are seeing that almost 2.1% of the CW flow is required. Of 2.1% of the total and comprising 1.7% EB loss and 0.05% is a drift loss and 0.35% is the blow down. So total is 2.55%. And the rest based on the transportation modes of the ash handling, blow down will be used, and based on that COC can be changed. So now since I am going to talk about the wet cooling system mainly, so for that direction I am just explaining. In the CW system we have one screw and recirculation. One screw only for the coastal area, and based on the discharge thermal impact on the seawater, it is restricted for a particular reason. Now coming to the recirculations, we have wet, hybrid and dry. So wet, dry cooling system has already, for the air cool condenser is already explained, and there are pros and cons is already explained. So in the dry cooling system is one side air cool condenser, other side is wet cooling system, where most of the client and most of the projects where water is in moderate condition, not very high, not a scarce. So if it is available where makeup can be done throughout 24 into 7 throughout the year, then wet cooling system is good because of the thermal efficiency has 7% output, power output is high, then CO2 is less, emission is less, capex cost is less compared to air cooled condenser. However, air cooled condenser is also in many places, even NTPC has explained that it is is installed in Jharkhand and other places successfully because of certain condition where water scarcity is very, very extremely high and no chances of going for wet system. It is very much feasible to get the dry cooling system, no doubt about it. But the wet cooling system where moderate water is available, this system is more feasible because thermal efficiency is high in this case and capex cost is also less compared to dry system, and then other technical aspects is there which is favorable for the wet condition. Now if we go to the wet condition, if you see the comparison, I am just making comparison. These are the sum of the for the dry cooling system, limitation, large footprint area, seasonal variability, efficiency variation, potential for land, heat land island, utilized increase in the ambient temperature because of air heat, air emission, airborne and land use impact. Other side, wet challenge is also is there, like water consumption, which I told makeup water will be very, very high quality. We have to maintain based on the LSI. The 0.5 or plus 2 or minus 2 based on that. So that treatment part our previous dignitaries are already explained. So these are the condition, technical condition, but main economic aspects where we are finding that dry cooling system is comparatively in term of thermal efficiency it is reduced, in term of generation it is reduced, in term of CO2 emission it is high, in terms of CO footprint it is high, in terms of capex it is high, tariff it is high. So clients see on that aspects also. So we have to make a balance between the wet system and dry system where we have to go dry and wet. If water is available and coal is also available, we will definitely go as previous speaker has told, respected speaker. So definitely wet system is good. But even we are knowing and for the down the line 34 days, no water scarcity is going to come. Then the question comes for the air-cooled condenser. Decision can be taken based on that economic factor and feasibility report. Okay. Now, coming to some scenario, how much water consumption and what is the pattern like coal? If you see water consumption is 3 to 3.5. Now it is reduced based on the CA. We have to limit up to 3. So we are going to 0.8 to 0.7 based on the other mode of transportation ash and what are the used for cycling makeup where designing for 3%, 2% water. And then, so we see the gas per by third consumption is either little or maybe very less. Nuclear slightly higher than the thermal and hydro little or almost no. So and this is the renewable where almost 0.1 to 0.2 per megawatt hour. So these are the this consumption we have 80% annually wet cooling system because in the now ash handling system is not like 20 years back. Now all the fly ash we are taking it by the this dry mode and bottom ash also whatever the consumption will be there only 70% will take back. So no question of much water scarcity, water resource in the ash handling. Mainly is 80% wet cooling system. So in that system, how much in that system, what is the advancement we can achieve and reduce that 80% to 50% to 40%. Means 80% out of 80%, we will reduce 50%. Like if it is, hello, if it is 80% for the CW makeup. So out of 80%, if you will reduce it to 50%, out of 80%, means suppose for the 800 megawatt, 3000 is the makeup. If we are able to reduce to 1500, that is a huge quantity. That is a huge quantity. And it is already existing 237 gigawatt is there. If we are able to achieve that and putting all the existing plant, that will be revolutionary step and will resolve the water crisis. Okay, so what is the advancement? First advancement is we are going to first advancement is the blow down reduction. Okay, how we are going to do? There are various methods. and their system is somewhere in place, somewhere they are putting efforts to get it more viable, to get it more competitive, so that everybody in the market they can go for this technology. So in this technology, what is the main thing? One equipment is there which can be installed before the condenser, right? So when this equipment will be installed before the condenser, how it will work when the water will come? So water will act as a catalyst, and inside the equipment, one core will be there, which will be highly electronegative elements. So when electrolyte will come, so this highly electronegative element will start precipitate the calcium and magnesium. As we know, the calcium and magnesium nature and the characteristic, when temperature will increase, precipitation will increase, dissolveness will reduce, and when also pH will increase, their precipitation characteristic will increase. Though this technology will enhance the formation of the colloidal particle, means characteristic of the calcium and magnesium, this calcium and magnesium, to get it precipitated, that nature is going to change because of the increased temperature and increased pH. Because one instrument is there, one metallic highly electronegative element will be there, which will attract H plus ion from the electrolyte. When H plus ion will be electrolyte, we know pH is inversely proportional to 1 by H. When H is attracted, pH will increase. When pH will increase, so in that particular equipment, precipitation will be there. And inside the equipment, there will be turbulent flow with high speed. So the calcium and magnesium will become, it will not precipitate, it will become colloidal particle, and it will not stuck inside the condenser, it will go past with high speed and will come out. So in that way, blow down, COC can be increased to a level to 5 to 6 to 7. So as you go further, 5 to 6, 7, 8, so obviously we know blow down will come down, because blow down EV loss divided by COC means. So this is actually in place, and it is not very known to everybody, known to every client, but it is in the market to some extent. Some parties are there on the western countries, and it is under the process of more evaluating this thing, and in future it is going to be maybe many clients will discuss this and will take it further. So that is the one advancement which is available in the market. Second is so this is actually the advancement which I discussed, blow down reduction method. So we can see the with COC 5, what is the quantity blow down? 0.357, and with 7, 0.25%. So for a typical 2 into 800 megawatt, 660 meter cube per hour, which we are doing, it will become 440. So that is available. It is not particular anybody's advancement. It is available in the market, but it is not this fully aware to every client. So need to take it forward with corporations and to particular more this knowledge and information what is. Now coming to second advancement. This is second advancement. Second advancement is the vapor reductions, which evaporation loss is almost 1.5% to 1.7%. Okay, so in 1.5% to 1.7%, in 2 into 800 megawatt, 1.5%, where cooling tower capacity is 8400 meter cube, your evaporation loss will come around, for 1 into 800 megawatt, it will come around 1400 meter cube. Okay, so in that case, huge quantity of water, as I explained, for the evaporation loss is going to loss to the atmosphere. So in particular this advancement, as previous speaker told, you cannot stop the evaporation, because it will increase the efficiency of heat exchange. So evaporation is must. But what is the way forward? We are collecting the vapor and we are changing into condensed water. So there is some part of design aspects which we are working on, we are evaluating, and where we are very much sure that it is going to be a very revolutionary step and will reduce the evaporation as a whole water consumption. Even we are going to, if we are success to 50%, okay, if we can see here, advancement to, with conventional, suppose it is 1.85 makeup, so if I am able to reduce it 50% efficiency, then makeup will come down to 0.93. If further I am able to go further advancement and 70% if I am going to reduce, then our makeup will be 0.5. So for a typical 2 to 800 megawatt, initial quantity was 2640. 50% if I am able to do this, then 1320. If further advancement can be done to 70% reduction of the conversion of the vapor to condensed water, that will be 792. Means from 1.85% to going to 0.93% with 50% efficiency with 70% 0.57. We are not telling that we are going to achieve 100%. No, it is not possible. So even 50% we are able to achieve with this technology. Our makeup is coming down to 0.93. It is in percentage less, but total quantity, if you see 2640, we are reducing to 1320. Okay. So this is the second advancement, and this advancement is under process, under evaluations. There are 4 factors of this to suction pressure and some chemical dosing and some vacuum system. So we are working and integrating it with our TC, and we will take it forward. It is still under evaluation stage. So this is second one. So coming now, third one. This is third one's advancement of the integration with the meteorological data. How? Because the cooling tower system we are operating, and this we are operating in a conventional way, that our fan is rotating with a particular RPM day and night. Nobody is going to see. Sometimes it is maybe changed, modulated. But based on the artificial intelligence and other advancement, now it is possible to collect the data of meteorological data like wet bulb temperature, dry bulb temperature, relative humidity, and one like how we do for the water transient analysis to check the characteristics of the flow water inside the pump house and check any transient condition or hammer condition during the plant operation. In the same way we are doing for the air. Okay, that is Renault, average, stock, theory. That simulation will be done for the air. Okay, and that air will, how it will be distributed based on the certain meteorological data that we are going to analyze with the simulation input, and the same simulation input is to be shared to the OEM of the fan. Okay, which based on the simulation input, fans can be designed based on their size, based on their blade dia, based on their axial angle. So OEM will design based on the simulation data, and meteorological data like wet bulb temperature, dry bulb temperature and RH, we will integrate it and interlock with this meteorological data with simulation input to the rotating fan of the VFD. Along with the VFD, without VFD it will not happen. VFD will operate based on the input data from the meteorological changes, variation in the day and night, any time, and based on the input of the simulation. So with these three, we will be able to reduce the fan consumptions. It will optimize the fan rotation, RPM, and based on the input, it will operate. So it will reduce here the power consumptions, but not only power consumption, Nowadays, question is, so many renewable sources are there, solar, wind and everything. So when it is coming, government is giving direction to operate your plant at the base load, even go further down, right? So fluctuation will be there in thermal and others. So how to resolve that thermal fluctuation of the load? So the answer is to operate with VFD. Fan also we need to operate. Also we have to operate the pumps. So with that concept, we will be able to save the power consumption as well as we will be able to save the water consumption as and when required. So this integration is under process also, and we are taking it forward. And with this advancement, it is not going to be huge saving, but 3 to 5% is expected to save in the electrical energy, power. And based on the power saving, your CW pumps can be modulated through the motorized valves, interlocking with the VFD and based on the meteorological data. So pumps also can be operated based on the loading condition. So this is the third advancement. And fourth one is, okay. Sorry. Yes. So in this the advancement third one, interlocking with the VFD fan, the interlocking mechanism adjusts the speed of the fan based on the real-time variation in the site data. Second one is optimization algorithm to determine the optimal speed of the VFD fan based on the measured environmental condition. Third one is control strategy. VFD fan designed to modulating the fan speed in response to the change in the meteorological data, wet bulb, dry bulb, and then relative humidity. Variable speed operations, operating at variable speed, precise control of air flow, adjusting the fan speed in real time based on the site data. So here one more thing is variable speed. This will be achieved based on the simulations. Okay, based on the simulations model, whatever input will come for the distribution, air distribution field, that has to be integrated along with the OEM. And then this data can be interlocked with the DCS to get the input from the meteorological data and operate the fan based on the demand. So that is the variable speed operation. Fourth is energy saving. Energy saving can be achieved by reducing fan power consumption, lower cooling demand, environmental conditions are favorable. Feedback control, the feedback mechanism to ensure that the desired set points are maintained, and monitoring and analysis by integrating the data with the operation of the VFD fan and implementing an optimized control, the strategy significant energy saving can be achieved. So this is the third one. Now fourth one is this side, floating solar panel. Floating solar panels is there everywhere and people are going through it. But in case of a specific power plant, we have a raw water reservoir, and for a typical 2 into 500 megawatt, we use at 20 to 25 acres land. And each acre of land can produce 0.35 megawatt solar through solar panel. So for 25 acres, we can produce 6 megawatt per hour. Yes, it cannot produce continuously 24 hours based on the climatic condition and intensity of sun. Okay. So, but it can produce to a substantial electricity which will be used for the advancement 1 auxiliary power consumption and advancement 2. So, what we have done advancement 1 and advancement 2, that only CAPEX will be involved. OPEX is not required. Because for OPEX, we are providing this solution where this energy can be used for the vapor reduction and for the blowdown reduction. So no energy is required, no operating cost will be required if we use this raw water reservoir as a floating solar panel. So here only not we are saving the electricity, we are saving water also. Because a raw water reservoir, open raw water reservoir in lean season, March, April, May, June, is almost 3 to 5% evaporation loss. So, now we are doing one project 2 into 100 megawatt. Daily per day, 120, 100 to 120 meter cube evaporation loss. Can you imagine? So when we are putting floating solar on them, evaporation loss also will come down. So if we are able to save at least 50 to 60% evaporation loss by putting solar, that also conservation of water, right? So in this method, we are reducing water consumption also. Producing one electricity, that is one part, which will be used for the advancement 1 and advancement 2. And in advancement 1, 2, there will no any additional auxiliary power consumption and it will not disturb any power generations. It will be compensated through this raw water reservoir floating panel. And through floating panel, we will be able to reduce the evaporation loss to extent of 50 to 60%. When we are able to reduce the evaporation loss, we are almost saving 50 to 60 meter cube per day for a 2 into 800 megawatt. So can we assume 60 meter cube into 20 into 30 into 12? It is huge. So many things can be done with this 4 advancement, and we are sure that down the line we are working, we are evaluating. One day will come where people will say wet cooling tower system is more efficient, and here is also we are now able to reduce the water consumption up to 2.1 meter cube per hour to 0.6 to 0.7 meter cube per hour, even 1 meter cube. So fine, this wet cooling tower is the solution. In the areas where water is not severely crisis, but there is a water available which can be taken out throughout the year, but it is not very huge water. So with the moderate water availability, wet solution will be a very good solution, because as terms of capex, opex and everything, it is more viable based on all the aspects. So these were the 4 advancements which I had done, and this is the solar panel which I want to show. You see, for 2 into 500 megawatt, 20 to 25 acres land, 1 acre land 0.3 megawatt per hour, 25 acre land almost 7 megawatt per hour. But this will not be continuous, because it all depends on the intensity of the sun and the season. So, but we can consider the 5 megawatt at least will be produced. As an average day, 4 to 5 megawatt. That will be more than sufficient for the other advancement of the power consumption. Now, process no loss of available land space, because we don't need land already available. So don't require valuable land, and scarce land can take up unused space on the bodies of water, reduce the need or to tree removal and forest clearing. All these things will be not there. Exploring solar plant in raw water reservoir will not only generate the additional electricity, but it will also reduce the natural evaporation loss. Hence, it will act as a dual conservation source, water and energy. So these are some advancement technology program reduction. This is overview. This is title. This is overview for this system, and this third system integration to the meteorological data. Fourth is, so because of time constraint, I am not able to focus much on the last slide. And these are the system which is covering for this actually benefits. We can see the scale reduction technology, preventing scale buildup in the condenser and all piping, minimizing scale formation, improved efficiency for vapor reduction, converting vapor to condensed water, designing to capture vapor by maintaining desirable condition to undergo a suitable process, forming liquid water that can be collected, returned to the cooling tower basin, reduces evaporation loss, saving substantial water. Real time for the integration of meteorological data, real time adjustment with the meteorological data, dynamic control and precise optimization of water and energy usage during the periods of lower cooling demand of favorable weather conditions. Cooling system can be operated at a reduced capacity, conserving both water and energy. Conversely, during peak cooling demand or adverse weather condition, cooling system can adjust operation. And 4.1 is the integrating of the raw water reservoir with the renewable energy generation system, which I have explained. So these are the way forward. Now, okay, proactive collaboration. What is the way forward and emphasis and recommendation? Recommendation is proactive collaborations and among the stakeholders, all the stakeholders, among the government body to all PSUs and big corporates, fostering innovation and adopting a holistic approach to implementation. Prioritize the investment in research and development of all this kind, incentivizing the adoption of sustainable practice and providing support for the deployment of advanced technology. Conducting comprehensive feasibility studies, engaging in strategic partnership with technology providers, and investing in workforce training to ensure successful implementation and long-term sustainability. Moreover, ongoing monitoring, evaluation, and knowledge sharing are essential for identifying opportunities for the improvement and scaling up to successful initiative. All this advancement. Embracing this recommendation, industry can realize the full potential of advancement in cooling water system and optimization and contribute to a more sustainable future, not only for the industry but for all the humanity, as you are seeing on the right side. So from the first picture to last picture, our kids will be enjoying with the water. So that is the approach for the 4 advancement to reduce the water, not only for the productivity or industries but also for the humanity. Thank you. Thank you.
innovations in this subject, and also the new R&D being taken place. So this is a very good indicator of our future, that we will be progressing towards the saving of the water consumption in very water intensive industry, that is thermal power plant. And I will have one or two questions from my learned speakers. They are the expert in their subject. So first my question will be from Ansari. So can you little bit elaborate how you made that decision to go for the air condensers?
Sir, the decision. So the decision to go in for air-cooled condensers at NTPC North Karanpura was basically because there was water available, there was a dam there, but then there was an option that suppose we go for air-cooled condensers, the water of the dam will be available to the local people. So keeping that in mind, company went in for air-cooled condensers so that the water which would have otherwise gone to NTPC only could now also be used for the community. That was the primary reason. Because water being scarce in that region, we said we'll take the hit. So you have seen in the presentation, the specific coal is higher and the back pressure, condenser back pressure is also poor in that case when we go for a ACC. But of course the specific water improves drastically. Because no, as we have all seen in the other presentations also, see, as per the MOEF guideline 2015, December 2015, it was given that a certain amount of water is only available for the thermal power plants. The norm was 3 liter per kilowatt hour, 3 liter per megawatt hour. So out of that norm, approximately 2 goes for the condenser cooling systems, C2 system only. So when that was the consideration, if in this case, we have also gone for an air-cooled condenser at Patratu. Again, Patratu is also in the same region where water is scarce. That is the basic primary reason.
Thank you very much. What challenges you foresee when it will be in operation?
Sir, already at North Karanpura, one unit was operational. Another unit has come into operation recently. And we are observing no challenges that way. Because the only challenges that are there is that during construction, more space is required. as compared to a conventional water-cooled condenser. We have already seen that the space requirement is huge. 132 meter by 132 meter is the requirement of the air-cooled condenser, and the vacuum obtained is lower. What is happening is, since the vacuum obtained is lower, the steam which could have achieved more work in the LP turbine is now constrained. So some amount of output is lost from the LP turbine. But that is the decision we have made when we went in for air-cooled condenser. Thank you, sir.
Sir, thank you for this question. As I think Dr. has gone, he has very elaborately told that TOC as per the EP guideline we have to monitor, and it is to kept below 100 ppb in our stream. So it cannot be done as such in the boiler itself. We have to control in the water body system, starting from the low water. This TOC analyzer we have in R&D where I was working, but in our this Jhajjar, we don't have the TOC. But based on our KMNO number, we are weekly basis we are monitoring in terms of there is a thumb rule between the TOC and KMNO 4, 1 to 4. If one KMNO 4 there, TOC is around 4. That is a thumb rule. In addition to that, in our CW program, which is given to some outside vendor, we are monitoring the TOC in the makeup as well as in the CW system fortnightly through some external enable agency. And in our makeup, it is around 2 to 3 ppb TOC, and in our CW system, it is 10 to 12 TOC is there, which we are monitoring throughout, and we have made the chart. And this fluctuation is not there, barring some time, and it has definitely detrimental to our the system. In just to share, if you give 1 minute, I'll just tell you a case study, and that was a havoc for us in December. There are the two reservoirs actually in Jhajjar, Reservoir 1 and 2. We had planned in last September to clean the Reservoir 2, and we have made it almost empty. I caution my operation fellows that whenever you are doing or when you are touching very low level, please tell me so that we can monitor the parameters. But unfortunately, I was on leave and my fellows or operation fellows did not converse between each other. And when I came back, they have started utilizing that Reservoir 2 water whose bottom was nearly touching. And because of that, what has happened, TOC level or organic level has reached to such a level that my plant was at the verge of shutting down. What has happened? Because TOC, because of its nature, it passes through our water body system, through our resin, and in boiler, it has a tendency to breaking down into the acidic components. So, because of those formation of the formic and those acids, our ACC, after cation conductivity, that started shooting up. So, what we do, once we see the ACs rising, we monitor the chloride, we monitor the sodium, because that may be sources from the some raw water, etc. Simple. We start with that only. We change the resin, but then pH of the boiler started going down. These are the detrimental effect of the TOC, which we have faced. We have heard it, but we faced it in December. And for our MS team, I think 0.8 ACC is the limit when we have to go for the action plan 4. That means we have to shut down our plant. And we have reached around 0.7, just measurement condition. But then I took a decision. I called my fellow chemist and just asked to carry out the KMNO 4 study, because we did not have the TOC analyzer. KMNO 4 number we determined, and based on that, I immediately make it out that in Reservoir 2, this KMNO 4 number of TOC or organic content has reached very, very high level. Immediately I went to the CO and asked him. CO said, I am not convinced, Sharma ji, you have to convince we have to change the water source from the reservoir 2 to reservoir 1. They listened me, immediately they changed the source, and within, I think, 6-7 hours, situation got starting normalizing. So that level monitoring is needed. Sir, you have very rightly pointed out, TOC is an analyzer which all the plants should have and organics to be monitored. We survived luckily, but this might have gone into catastrophe.
Thank you. Because TOC online monitoring, if you are doing, indirectly you are saving other challenges.
Yes.
Okay, and it is a PPB level,
PPB,
available
yes.
online.
Yes, sir.
Okay.
So we are going for that online analyzer also.
Nice.
Thanks.
Thank you. So my last question is from Mr. Sohail. You are doing very good research and very good
Thank you, sir.
additional
Yes.
advancement you are suggesting.
Yes.
Have you any trials or some pilot plant or how you are doing?
Sir, it is under it is under concept is developed. It is under evaluation stage with our R&D team with NTC. So still pilot plant is not reached, but we are in the process to get it. Within maybe 6 months, we'll be in a position to develop it.
And will you plan to automize all these parameters so that you can very optimally
Yes.
control the flow
Yes.
and other parameters,
Yes.
temperature, and you can have better output.
Yes, sir, you are right. Because of the fluctuation in demand, sir, because of so many renewable energy sources are now executed by so many players, and in future, so even government prospects to go through renewable. So all the existing as well as whatever new will come for thermal, they cannot operate for a full load. So they have to operate based on the part load directions from the government and the bodies. So in case of fluctuation of the load, we need to have a moderator which can modulate the flow, which can modulate the air flow, which can modulate the water flow. So for that we need integration and interlocking between the different field of parameter, like one is meteorological data, they are coming wet bulb temperature, dry bulb temperature, relative humidity. Other is required a Reynolds average stock method simulations for the airflow. How we do for the transient analysis, and we analyze whether flow is turbulent or whether it is steady nearby the suction sum. And if it is required to put something to reduce the swell angle and to reduce the turbulent, we used to put some recommendation like flow straightener and other thing. In the same way, they will analyze in that simulations how the air can be optimized for the VFD. So with that input simulations and with the meteorological data, we will integrate it, will interlock and will send the feedback to DCS. Based on the input, VFD will act. If required, pump will also can be modulated. So in that way, we will operate and it can be defined. What you told, sir, that is 100% right. We should integrate all this parameter along with this rotating equipment so that it can be optimized. Correct, sir.
Thank you very much. So now my one question to you. What are your views on the hydro turbine to recover the pressure energy which is wasted, which can be recovered up to the 40 to 50% at least? There is a pressure energy also. Due to loss of the pressure in the overall system. So if we can recover that pressure energy through hydro turbine, so do you have any idea of that? Or has it been implemented?
We have, basically, sir, a small hydro has been installed at the CDU system at Simrodi. So we have done that.
Good.
At NTPC.
So what is your experience?
5 megawatt hydro turbine is installed at CDU Simrodi.
Okay. So you find some worthiness in that?
Yes, sir. Definitely we are getting additional 5 में तो
Yeah. So that's why I'm saying there is a loss of energy, pressure energy, which can be recovered. So because nobody is talking about that, that's why I raised that question. Because you are the expert in this industry, so you can also think of that. So I now open to the audience for your questions if you have from any of the expert speakers.
गुड इवनिंग टू ऑल सर, मैं प्रभात कुमार चौधरी NTPCAPCPL से हूँ। 10 साल पहले 300 मेगावाट का हमारा एक यूनिट था, उसमें हमने ACC लगाया हुआ था। ये लगभग 2013 के आसपास हमने इंस्टॉल किया था। जैसे कि वहाँ हमने पाया समर सीजन में जो वैक्यूम आता है, एक्चुअल में डिजाइन वैक्यूम है 78 kVA का। समर सीजन में जो आता है वो घट के 74 हो जाता है और विंटर में 80 करीब मिलता है। तो इस गैप को कैसे कम कर पाएंगे?
सर इनफैक्ट तो जैसा आप बता रहे हैं एम्बिएंट एयर टेम्परेचर जो है विंटर में कम होता है, इनफैक्ट विंटर में आपको बेहतर मिलना चाहिए।
बिल्कुल मिलता है सर, 0.80 हो जाता है। 78 का उस KPA का डिजाइन है, वो 80 KPA करीब आ जाता है।
अच्छा।
लेकिन समर में घट के वो जो है 74 हो जाता है।
तो सर समर में तो घटेगा ना, एम्बिएंट टेम्परेचर का जो आपका डिजाइन टेम्परेचर है एम्बिएंट का वो बढ़ गया है, तो अगर परफॉर्मेंस उसका डिजाइन से पुअर हो जाएगा तो नेचुरली
नहीं वो
कम हो जाएगा।
नहीं, मेरा क्वेश्चन ये था गैप को कम करने के लिए कोई और अपन टेक्नोलॉजी यूज कर सकते हैं क्या? जैसे मिस्ट सिस्टम है, अगर मैं मिस्ट सिस्टम को लगाता हूँ तो एयर टेम्परेचर डाउन होगा, तो उसका उपयोग कर सकते हैं।
सर वो तो एक और एडिशनल सिस्टम लगाना मतलब और खर्चा।
नहीं वो खर्चा जो है, लेकिन पावर जो जनरेट होगा उसको तो और कम पड़ जाएगा ना।
सर आपने एयर कूल्ड कंडेंसर लगाया था, ये ध्यान में रखते हुए कि पानी का कम होगा इस्तेमाल। अब आप मिस्ट सिस्टम लगाएंगे, अगेन यू आर गोइंग फॉर मोर वाटर कंजम्पशन।
मिस्ट में कितना बहुत कम लगेगा पानी, जहाँ तक अंदाजा
इस पे लगेगा ना,
लगेगा, लेकिन
I have seen that system where they have used, they are getting much more efficient than that. They are getting little bit out of that.
I have seen that this system, and where they are using it, they are getting benefit out of that. During summer.
What he is trying to say is they are getting poor vacuum. How to control that? So
To overcome that, to reduce that gap, they are using this system. I have seen that because they are using the this system just like that for horticulture. They are using, instead of that they have put nozzles over that, and pipeline is there, and on that different nozzles are there. From there they are getting water, and when this fan is there that sucks that water, that I have seen that mist is going over there and reduce the temperature, and they are getting much more efficiency. Their vacuum is improving. Okay. Any other question?
Any other questions? Else I think we are good to then conclude this panel.
Good, if there is no question. So we thank to all the speakers. Thank you.
Thank you so much. I request you all to please step forward for a group picture. We can keep the applause going, and I would present a token of gratitude to each one on the panel. May I have the mementos, please? Thank you. Thank you so much. Requesting the panel to please take your seats and requesting for the chairs to be cleared from the stage as I move on to announcing the next panel and discussion and set of presentations that we're going to be having. So this is going to be our last set of presentations for the day, and the discussions and presentations are going to focus on wastewater management and zero liquid discharge and seawater usage. I would now like to announce the presenters and speakers and introduce them to each of you along with the moderator, and then we would also have them join us on stage in a similar format where we have the discussions going on. I would like to begin with welcoming Mr. Ex-CPCB, Partner, Government and Public Sector, Strategy and Transactions, Ernst & Young LLP. He is going to be the session opener and the moderator. Before I welcome him on stage, a few more words about him. Mr. Jain, a seasoned infrastructure professional and partner at EY, brings a wealth of experience across diverse sectors, including water, sanitation, irrigation, economic corridor development, oil and gas, SEZs, real estate housing and industrial parks. His dynamic role involves spearheading initiatives and fostering collaborations with a wide spectrum of stakeholders, including national and state governments, multilateral and bilateral banks, research institutions, private sector entities, industry associations, and NGOs. Mr. Jain's current focus centers on advancing the reuse of treated wastewater, aligning with critical national programs such as Jal Jeevan Mission, NMCG, and Amrut. Furthermore, he is deeply committed to tackling climate change challenges and driving impactful public-private partnership transactions within the water sector. Also, now I'll announce our speakers with their profiles. We would also have a presentation by Dr. Girija Bharat, Managing Director, Mugama Consultants. Dr. Bharat is an international expert with 33 years of experience in water resource management, water supply and sanitation, chemical pollution control, persistent organic chemicals, and environmental management. She has collaborated with institutions like TEDI, USAID, and the World Bank. Dr. Bharat has contributed to 129 national and international publications, including the Global Sustainable Development Report 2015 and 16, and co-authored the National Policy Framework of India on safe reuse of wastewater. She is a Research Council member of CSIR NERI and a technical expert of the Managing Organization Vertical of Niti Aayog, Government of India. She is a member of the American Chemical Society and Iota Sigma Pi and Honors Society for Women in Chemistry in the US. Dr. Bharat was the recipient of the IIM Bangalore Goldman Sachs 10K Women Entrepreneurs Program 2021 and has received several awards, including Women Transforming India Award by Niti Aayog 2021, Global Environment Award 2020, and the Exceptional Women of Excellence Award of Women Economic Forum in 2019. Our next presenter will be Mr. Shailendra Kumar, AGM Project Management Group at L&T MHPS. Mr. Kumar is a seasoned project and construction management professional with over 21 years of hands-on experience in delivering top-tier greenfield projects, including solar heat recovery boilers and pulverized coal-fired boilers and turbine packages. His expertise lies in ensuring projects are completed within defined time, cost, and quality parameters while fostering effective collaboration within project teams. Throughout his career, Mr. Kumar has successfully managed various aspects of projects, including pulverized coal-fired boiler and auxiliaries, heat recovery steam generator and auxiliaries, turbine and auxiliaries, coal handling, water and wastewater treatment, air handling, and fuel oil handling. Having worked with renowned organizations like Busan Power System India, Acme Heating Solution, JK Organization, Jindal India Thermal Power, Reliance Energy, JSW Energy, and Bharat Heavy Electricals, Mr. Kumar brings a wealth of experience and a proven track record of project success. Also introducing Mr. Prabhakar Ilumalai, Assistant General Manager at Tata Consulting Engineers, with over 23 years of experience in chemical engineering. He specializes in water and wastewater treatment. From his roots in the textile and pulp industry to stints abroad and at prestigious